Hello everyone, this is Tarun Malhotra, lead software engineer here at InterviewBit. Welcome back to the dynamic programming sessions that we are having. I hope you guys liked the first video, and today we are going to take our discussion up, take our discussion from there and discuss some more interesting problems and try to build an intuition that how you would be able to solve any problem that you see for dynamic programming, and how would you able to solve any such problem. What is the way to approach any DB problem? Okay, cool. So I would just reiterate a couple of things that I said in the last class. I said that problems which can be solved using dynamic programming show two primary features, right? One such feature was that the problem is going to show optimal substructure, and the second property that the problem is going to show is going to be of overlapping subproblems. Just taking a minute to redefine these things. So optimal substructure basically mean that you are trying to solve an optimization problem. You want to find an optimal solution to a bigger problem. You can figure out the optimal solution to that bigger problem using the optimal solutions to one or more smaller such problems. Okay, so you can figure out an optimal solution to a bigger problem using the optimal solutions that you have for one or more smaller such problems. This is what is called as the property of optimal substructure. The second property is overlapping subproblems. Overlapping subproblems means that yes, you have actually, so this basically in a way means that you can define a recurrence relationship to solve your optimization problem. Overlapping subproblem basically mean that okay, you have defined a recurrence, you can very well solve your answer, get an optimal answer using a recurrence relationship, but you can also see that so many of those states are going to be repeated, right? You are going to see so many states which are being repeated again and again, and you would want to utilize that information, store it somewhere so that you avoid recomputing the same states again and again. Okay, so this basically takes you from the recurrence, brings you to DP, because you are avoiding recomputing same states. Cool. If you keep this in mind, theoretically, you know what DP problems are. Okay. Now let's try to actually build upon that and solve several questions and see how very intuitively you can answer any question. Use any question which can be modeled into DP. You would be able to model it if you just go through these videos. Okay. Cool. So let's look at the first question of the day. The first question of the day is as follows. You are, let's say, given a n. Okay, you want to figure out the number of bit strings of size n following a condition. Okay, so let's just take it one by one. You are given a number n. You want to figure out the number of bit strings of size n following a condition. Let's forget about the condition for now. Let's simply look at n and number of bit strings. So what is a bit string? A bit string of size n is a string of size n where every element is either going to be 0 or 1. Okay, so a bit string is simply a string where every element can either be 0 or 1. Okay, cool. So let's try to solve a very trivial question. First of all, if you're given a n, can you figure out the number of bit strings of size n? Is that very easy to solve? Yes, that is very easy to solve, because let's say if you have n is equal to 3, what does that mean? It means that you have 3 places to fill. Every place can either take a 0 or a 1. So every place basically has two options. And irrespective of whatever option I take here, I still have two options for the second element. I still have two options for the third element. So basically, the number of options that I have is 2 into 2 into 2, and this will repeat n times. So basically, the number of bit strings of size n would be 2 power n. I hope there is no doubt till here. The number of bit strings of size n would be 2 power n. Okay, cool. Now, once this is done, let's now look at the specific question that we had. The specific question that we had was that we want to figure out the number of bit strings of size n such that no two bits, no two consecutive bits are ones. What does that mean? That means that there are no two consecutive ones in the bit string that you have. Is this clear to everybody? Can I actually look at also the comments? So if you have any doubt, you can post them in the comments, and I would be more than happy to take them up. Okay, cool. Which language you use, that is not a thing that is going to cause any material difference to your understanding. So do not worry about that. We are discussing concepts here, and the concepts I am promising would be crystal clear after looking at the video. Okay, cool. So yeah, so we were now discussing that the question is you want to figure out the number of bit strings of size n which do not have any consecutive ones. Okay, cool. So let's try to figure out the number of such bit strings. So let's look at n is equal to 2. So basically, you have two options to fill, and you cannot actually have consecutive once. Okay, cool. So here we are going to do that. So here, just wait, hold on for a bit. Let me just complete with this so that everybody's on the same page, and we are going to move to tougher problems as we go along. Okay, cool. Right. So now 00 is a valid bit string which follows the definition that we have. 01 is 01 a valid bit string? Yes, 01 is also a valid bit string because there are no two consecutive bits with ones. Is 10 a valid bit string? Yes, 10 is also a valid bit string. Is 11 a valid bit string given the condition that we have? No, it's not valid because I see two consecutive ones. So the answer for n equal to 2 is going to be 3. Okay, now let's actually look for n equal to 3. When n equal to 3 you have three options to fill. 000 is perfectly valid, 001 perfectly valid, 010 perfectly valid. Is 011 valid? No, it's not because I see two consecutive ones being repeated. Then 100, is that valid? Yes, that's valid. 101 totally valid. 110 not valid because I again see two consecutive ones. And then 111 of course not valid because I see two consecutive ones. So the answer for n equal to 3 would be 1 2 3 4 5. So the answer to this would be 5. So we now know that for n equal to 2 the answer is 3, then n equal to 3 the answer is 5. Cool. Once we know that, now let's actually try to figure out a DP solution of going about it. Okay, before that, do you see optimal substructure here? What does that mean? If by chance you have the answer to a smaller n, let's say you know the number of ways you can build n equal to 4, can I somehow use that information to figure out the answer for n equal to 5? Maybe yes. Does that make some sense? So you can use, it seems from this question that you can use the answer to a smaller problem and try to figure out the answer to a bigger problem using the answers to a smaller problem. Okay, cool. Okay, it does seem that it does have some optimal substructure. Now let's look at some very, very interesting points that I feel that always help me while coming up with a DP solution. Okay, so first of all, you guys would realize that in DP you talk about states, right? You actually have a state for which you have an answer, and then you use that state to figure out an answer to a bigger problem. Does that make sense? Right. So it's important to look at states. So the very first thing that I generally ask myself is that what will a state represent in this DB solution? Okay. What will a state represent here? What does that mean? We will see in this question. What will a state represent here? The second question that I try to ask myself is what parameters are going to be there in a state? Okay. So to define that state, what params do I require? Okay. The third question that I try to ask myself is that what is the element of choice here? What is the element of choice in this question? Okay. What do you mean by element of choice? It simply means that what is the choice that you have to take so as to figure out the entire answer. Okay. So we'll see it one by one. First of all, let's come back to this question. You want to find the number of bit strings of size n with no two consecutive ones. Cool. Now, what will a state represent here? Okay. So let's say I come up with a state which is dp of, let's say, I, which actually represent that if I had a n size bit string, let's say dp of I represent the number of ways I can have a bit string conforming to this definition from the from, let's say, the zeroth. Okay, so let's say there are two ways to go of going about it. You can either build it from left to right, or you can build it from right to left. Let's try to see that we would want to keep on building from right to left, let's assume. Okay, so what would I say? I would say the number dpi is basically the number of ways you can have a bit string conforming to this definition, which starts from the ith index and end at the n minus 1th index. Does it make sense? So you have indices from 0 to n minus 1. dp of I, let's say, represents number of ways you can form a bit string which conforms to this definition, which starts from I and end at I minus n minus 1. Does that make sense? Does this state make sense, folks? dp of I means the number of ways you can have a bit string from starting from I to n minus 1, given it satisfies the given constraints that you had. Cool. Now, if this is what my dp state is, can you guys actually figure out what will be the global answer? What will be the final answer that you're talking about? So dp of I basically means number of bit strings conforming to the definition above, starting from I to n minus 1. Right? If this is what my definition is, then the entire answer, which needs to start from 0, end at n minus 1, you would understand the final answer is going to be dp of 0. I hope it makes sense to everybody, because the final answer we would want it to start from the 0th index. So 0 to n minus 1 ke liye, dp of 0 would give me the final answer if this is how I am defining my states. Cool. So this, I now know that how a state is represented here. Now, to define that state, what params I require, that I also figured out that we require a single parameter, which is I, which actually here means the starting point. Cool. Now let's discuss what is the element of choice. Okay, let's now discuss what is the element of choice that I have. So you guys tell me, what is the element of choice that I have at the ith index? Would you agree with me that I have two elements of choice? I can either fill a 0 here, or I can fill a 1 here. I hope it makes sense to everybody. I have two elements of choice here. Either I can fill a 0 or I can fill a 1. Cool. If I fill a 0, now I need to figure out how does my question change thereafter? Okay, if I fill a 0 here, how does my question change thereafter? So let's assume I'm filling a 0 here. Does that impose any condition on the remaining answer? Does that impose any condition on this bit or this bit or this bit? It does not, right? Because my question was that I cannot have two consecutive ones. So the moment I fill a 0 here, I'm not imposing any condition on the following bits. Okay, so it means that if I'm filling a 0 at this position, the remaining things can still have all the possibilities that they had before. So I can say that I am reducing my answer to dp of I plus 1. Does that make sense? I am saying that if I just put a 0 here, the problem that I have is to find a number of ways would still be dp of I minus 1 only, because whatever is there pending thereafter, you have not imposed any new condition there. Okay, so it's dp of I plus 1. The second option that you had, what if I filled a 1 here? Okay, what if I filled a 1 here? If I filled a 1 here, do you see I am imposing some conditions thereafter? Yes, I am, right? If I fill a 1 here, what am I imposing something on the I plus 1th index? I am, right? If I fill a 1 here, the I plus 1th index must be a 0, because it cannot be a 1. The moment the I plus 1 index also becomes a 1 when ith is 1, it simply means that you have not conformed to your definition. Okay, so this must be 0. Now I am imposing a condition here at the I plus 1th index. Do you see myself imposing any condition on the I plus 2th index, folks? I'm not, right? Because the moment I fill a 1 at the ith, 0 at the I plus 1th, the I plus 2th would simply can take again a 0 or a 1. I'm not imposing any condition on I plus 2. I hope it makes sense, right? So if I'm filling it at I 1, then at I plus 1, I must fill a 0. At I plus 2, I can fill anything. So my problem actually reduces to saying that I am filling a 1 at the ith index, which has one way of solving it, multiplied by I am filling 0 at the I plus 1th index, which is again one way of solving it, multiplied by dp of I plus 2, because I plus 2 can still take all the possibilities, and that is a subproblem that I have. Does it make sense to everybody in the room? Hello, folks. Can you hear me? So the point is ki it's rainy season out here in Bangalore, and we are facing constant power outages. And the society does have a backup power, but the moment the power goes and they actually have to switch, when they switch, it actually goes down for a couple of seconds, and then the router restarts, and that's the issue. So I'm very sorry for this. Very sorry for this. Poor user experience, but this thing was not in my hand. So just give me a minute. I'm just reconnecting to my Zoom video call so that I can share my screen with you. So just hold on for a bit. Okay. In the meanwhile, you guys can tell me if you are able to understand what we were discussing. And the reason why I am actually spending so much time in discussing a simple question was because it gives you insights as to how to solve any problem. any DP problem. And if you, what my belief is, if you spend enough time on some basic problems, figuring out the concept very well, you would be able to solve the complex problems also relatively easier. Okay, so just hold on for a bit. Let me just connect to my Zoom call, and then we can continue. Let's just hope the electricity does not play games with us again. Okay, cool. So I hope the screen would be okay. Let me just make sure that the screen is visible to you guys. uh, just a minute. Cool. Cool. So I hope the screen is visible to everybody. And let's continue. So we discussed that yes, here we have two options here. One option is that I can either have a zero at the ith index, or I can have a one at the ith index. If I have a zero at the ith index, it simply means that I am having a zero here, one multiplied by whatever is remaining can still take every possibility. So dp of I plus one. Or the other option that I have is fill a 1 at the ith index. The moment you fill the 1 at the ith index, the I plus 1th index must have a 0. So 1 multiplied because you want to have 1 at the ith index, 0 because you want to have 0 at the I plus 1th index, multiplied by dp of I plus 2, which simply leaves you with the remaining problem. And these are the two options that you had at the ith part, either to fill a 0 or to fill a 1. Now, one very interesting thing that you guys should know, that these two options that I had, 0 and 1, these two options are nothing but mutually exclusive plus mutually exhaustive. What does that mean? That means that mutually exclusive means that if you are filling a 0 at the ith index versus if you're filling a 1 at the ith index, no matter what you do thereafter, these two bit strings are going to be different. Does that make sense? If I'm filling a 0 at the ith index or I'm filling a 1 at the ith index, no matter what happens thereafter, these two bit strings are definitely going to be 0. So that's why mutually exclusive. Then the other thing is mutually exhaustive. Mutually exhaustive means that there is no other option other than filling a 0 or 1. If you just take into account filling a 0 and take into account filling a 1, there is no possibility which is left outside the scope of filling 0 or 1. Okay, the moment you see that your states, that your possibilities are mutually exclusive and exhaustive, you can simply consider that considering these two things is going to not overcount and neither undercount. Right, whenever you say it's mutually exclusive, it means that you are not overcounting. So it means you are not overcounting. Whenever you see it's mutually exhaustive, then it means you are not undercounting. I hope this thing makes sense to you guys. This is very important. Okay. So okay, cool. Now this is what we have. Just because these are mutually exclusive and exhaustive, you can simply now add these two things and you will get the entire answer. So your entire answer looks something like this: that dp of I can be reduced into 1 into dp of I plus 1, which is you were filling a 0 at this point, or you can fill a 1 at this point, which will make it 1 into dp of I plus 2. So this is the recurrence that I have seen, and this actually solves the entire thing for me. Okay, does it make sense to everybody? So this actually solves the question for me. I have got the recurrence relationship. And look at the 3 points that I mentioned. I utilize these 3 points to understand everything about the question, and I've figured out a solution to it. Now, the only thing that is remaining is that once you have a recurrence relationship, you need to figure out the base cases, because base cases are those cases which are trivially easy to answer, and you would not want your because your recurrence would not be able to define those cases, and those are trivially easy to answer. So you would want to define them yourself. So looking at this recurrence, can you figure out what cases is my recurrence not able to define? You would agree with me that one such case is dp of n minus 1, right? Because this recurrence to work, it requires I plus 1th and the I plus 2th index. And for n minus 1, n does not exist, which is I plus 1, and n plus 1 also does not exist, right? It's 0 to n minus 1 indexing. So dp of n minus 1 will not be able to explain using this recurrence. So that's a base case that we want to define, which means that you have only a single element, because n minus 1 would be a single element. Number of ways that you can fill a single element given this definition, we already solved that. That for n equal to, or we did not solve it, but for n equal to 1, you would realize that you have basically two ways. You can either fill a 0 or you can fill a 1 here, right? So you will say the base case dp of n minus 1 is equal to 2. Then let's say, is there any other state which will not be able to be explained by this recurrence? Yes, dp of n minus 2 will not also not be able to be explained, because it requires I plus 1 and I plus 2. So if that is also not equal to, we can explain. So you can say n minus 2, n minus 1. It basically boils down to having two elements. You can either fill a 0, 1 in both of them. So we figured that out, that 0, 0 is possible, 0, 1 is possible, 1, 0 is possible, 1, 1 is not possible. So for dp of n minus 2, the answer would be 3. So these are the two base cases that I have. Now let's actually look, can I actually figure out n minus 3 using this recurrence? Yes, I can very well do it. So that is not a base case. Does that make sense to everybody? Now I have a recurrence relationship. I can very easily write the code for it. Do you guys want me to write the code for it, or can you guys do it yourself? Just a quick, okay, there is slight delay in when I speak and when I can see your comments, but I'm just hoping that you guys will let me know if you want me to write the code. But I can assume that you can also take it as a homework exercise and you will be able to solve it. Okay, cool. Let's actually move forward. Let's actually move to the next question. I wanted to discuss another approach of solving this question, but I see that some of you already know this, and we can actually move to the next question in that case. Let's not spend more time in discussing another approach to this question, but I hope that this is crystal clear to everybody of you. Okay. Okay. Cool. Let's now move to the next question that we have. The next question that we have is this. You have a matrix of size n cross m. So you have a matrix of size n cross m. Okay, so I see 3 people who are saying write the code. So let me just do it. This is a very simple question. I will just write the code of this dp of n minus 1 is equal to 2, dp of n minus 1 is equal to 2. Yeah, that makes sense. dp of n minus, okay. So let me just write the code also here, and then I can move to the next question, because I see 3-4 people. But the point is, it's important to learn the concepts. If you want the codes, I can always attach them in the description of the video after the class ends. You can always look at those codes. But if you want me to write it right away for this particular problem, I can do that, right? So let's just do it. Cool. So this is a recurrence solution. This is a recurrence solution. Cool. So we would want to say, define a recurrence function int, let's call it solve. What will it take as input? It will take as input a integer for okay, so it will take as input the I for which you are solving it right now. So int I, comma, with that it will also include the dp state vectors that you have. Okay, so there are two ways here, right? Understand it. In the recurrence, you are only looking at the I plus 1th and the I plus 2th solution only. Does it make sense? You are not looking at anything else. You're only looking at by the I plus 1th and the I plus 2th solution only. But for now, let's assume we are having an entire array which stores every dp state from dp0 to dp n minus 1. Does it make sense? But you know that you can actually improve it and only have the I plus 1th and the I plus 2th solution stored. That is something that you can do using the bottom up solution. But I am doing the top down solution because I see several of you are asking for the top down solution. Cool. So int I, that is I am taking a decision for the ith index, and a vector, let's say, of integers, and let's call it dp. So basically you have a dp ka vector in which you are going to store everything that you pre-computed already. Okay. Before coming to this function, you would have to initialize this entire vector with, let's say, minus ones. Okay. So let's say you initialize this entire vector with minus ones because it means that this state has not been computed yet. And after that, you initialize the base cases. So you say dp of n minus 1, you can say it's going to be 2, and dp of n minus 2 is going to be 3. So you define these two things. Okay, cool. Now in this solution, you can simply say, first of all, let's do a sanity check, that what happens if the I that you have received, let's say you also had a n, that for which thing you are actually trying to solve it, what is the maximum size. So first of all, you check if the I is greater than equal to n. That is just a sanity check because this is never possible. This is never possible. So you can simply say return minus 1, that you have just given me a wrong input. Okay, cool. After that, I've already mentioned the base cases here, so I need not mention it there. Otherwise, I would have mentioned the base cases here. I hope you guys understand it. Whenever you are writing a recurrence relationship, you must first of all take care of the base cases. I have taken care of the base cases outside this function already, so I need not write it here. Cool. After that, what will I do? I will now just look at whether the particular DP state has been already computed or not. Okay, so I will say if DP of I is not equal to minus 1. What does it mean? It means that I've already computed that DP. If I've already computed that DP, would I want to recompute it? No, I would not want to recompute it. So what would I do? I would simply return DP of I. Does it make sense? Else, if I've not recomputed it before, I'm looking at this state for the first time. If I'm looking at this state for the first time, I will then solve it. So what will I do? I will then say, looking at the recurrence that I have, dp of I plus 1 plus dp of I plus 2. So I will say return solve. I will call this solve function for I plus 1 comma n comma dp plus solve I plus 2 comma n comma dp. Does this make sense to everybody in the class? That this is the code which is going to solve everything for us. Okay, and the initial call that I'm going to make to this function is going to be solve 0 comma n comma dp. Does that make sense to everybody? Cool, because the final answer is given by this particular state. I hope this is clear to everybody. We can move to the next question now. Cool. Let's come to the next question now. That you are given a matrix of size n cross m, and you now want to figure out. So for every index that you have, you can only go either in two directions. So let's say you are here. There are two options that you have. From any index, you can either go to the index on your right, let's say this index A, or you can go to the index on your down, which is B. So from every index, there are two options that you have. Either you can go to the index on your right, or you can go to the index on your down. There is no other option other than these two options. Okay. Now you want to figure out the number of ways to reach from the start to the end. Okay. This is very simple solution, that you just want to figure out the number of ways you can reach from the start to the end. And from every index, there are two possibilities that you have. Either you can move to the right index, or you can move to the down index. Does that make sense to everybody? Now this question is a very simple question to solve. Let's forget about DP and let's just try to figure out how you can potentially solve it. I would suggest that if you just want to figure out the number of ways, let's try to look at it from a PNC perspective. Okay, permutations and combinations perspective. You would realize that if I want to reach from start to end, I essentially have to make m minus 1 moves on the right, and I have to make n minus 1 moves down. Does that make sense? I want to make m minus 1 moves towards the right, and I want to make n minus 1 moves downwards. Okay? Now, does it matter in what order do I take these moves? I can potentially take them in any order. Does that make sense? I can potentially say that I will take all the down moves first. So I will go from here to here, from here to here, and then I will take all the right moves. Or I can say that I will take all the right moves first and then take all the down moves. Or I can say that I can just take a random sequence of down or right moves. So I can take a down, a right, a down, a right, right, a down. So you can essentially take any such ordering, and all of them are going to take you from the start to the end. So the problem actually boils down to figuring the number of ways to arrange these m minus 1 and n minus 1 steps. Does it make sense? So, people, there are m minus 1 steps to your rights. This is m minus 1 times. And you have n minus 1 steps to your down. This is n minus 1 times. You would essentially need to figure out any such permutation of these m minus 1 and n minus 1 steps would do all these things for us. Okay, so what do? I will simply permute all the possibilities. So I will say m minus 1 plus m minus 1 ka factorial. This will give me the permutations of all the possibilities here. You divide it by m minus 1 factorial and n minus 1 factorial. Why? Because m minus 1 of them are the same and n minus 1 of them are the same. Does that make sense to everybody? I hope it does. Right? So this solution will give you all the ways from the starting till the end. Okay? But still, I would want you guys to solve it using the DP approach. Why is that the case? We would still want to solve it using the DP approach because this solution, which was very simple, which is very simple, is very fine to do, but you can actually figure out some complex problems which you would not be able to solve simply using permutations and combinations. Does that make sense? Cool. So if this is what you already have, this you already know how you can actually figure out a DP solution. Let's try to look at it. Okay, again, remember the 3 steps that I told you before. There are 3 steps for any question in DP would be like this. The first step would be that what will a state represent? Second would be what all parameters do I require to represent a state? And third would be that what is the element of choice that I have? Okay, to answer these 2 first questions, that what does a state represent, you need to actually go back to the optimal substructure definition that we had. You want to represent your state in such a manner such that the solution to a bigger state can actually be utilized, can actually be computed utilizing solutions to smaller states. Does that make sense to folks? So you would want to define your states in such a manner that a solution to a bigger state can actually be represented using solutions to smaller states. Okay, so here my submission would be that again there are 2 ways, because this is a problem which is symmetric from both ends. I can either build a solution from the top to down, or I can build a solution from the last index to the first index, right? Both of them are equally symmetrical to me. I can choose any such option, but I would say let me define my state in this way. If I am I comma j, I want to reach this end. So let's say dp of I comma j represents the number of ways to start from I comma j and end at end. Folks, does it make sense? Do you see it as a very good candidate of representing a state? Because keeping in mind the optimal substructure that we had. If I know the solution to figuring out the number of ways that I can have from this cell to this cell, can I hope to utilize this to figure out the number of ways for, let's say, cells on towards the top right, top left? Folks, does it make sense to you? I'm waiting for you guys to reply, or I can actually spend some more time in explaining this, because this is very, very interesting, right? So you potentially are building a state keeping in mind the optimal substructure problem. You are building a state which will help you to figure out a recurrence relationship using this optimal substructure property. That you now have dp of I comma j, in my definition would be number of ways that you can start from I comma j and end at the end. Okay, I hope it makes sense. Cool. Now, if this is what I am representing my state as, let's try to look at. So we now know what is the state represent. We have figured that out. Second thing, what are parameters do I require? I figured that out. I comma j are the two parameters that required to represent a state here. The third problem that we have is what is the element of choice? Okay, so you folks tell me, if I am at this position, what is the element of choice that I have? Right? Or if I have at any position, what is the element of choice that I have? That is defined by the question itself. I have two elements of choice. Either I can move towards the right or I can move towards the down. Does it make sense to everybody? Does it make sense to everybody? Either I can move towards the right or I can move towards down. There are two options that I have. Are these two options choice element of choices? Either I can take a step or I can take a B step. Now you guys tell me, are these element of choice both mutually exclusive and mutually exhaustive? Yes, these are, right? Because if you take a right and if you take a down, no matter what you do thereafter, these are going to be two different approaches. Similarly, if you take a right and take a down, there is nothing remaining outside of this, right? Cool. So these are both mutually exclusive and exhaustive. Now we want to actually figure out how to utilize this element of choice to define the recurrence relationship. Okay, so I would say from dp of I comma j, I had two options, either to do a or a b. If I do a, what does it mean? I am actually going to a smaller problem, which is dp of I comma j plus 1. Does it make sense? If I am going from A to, if I'm going from dp of I comma j to A, it simply means that I am going to dp of I comma j plus 1. So I will say dp of I comma j plus 1. If I'm going to the B, right? If I'm going from I comma j to B, it means that I am reducing my problem to figuring out the number of ways of reaching from B to E. Does that make sense, folks? Number of ways of reaching from B to E. And that, by my definition, is going to be dp of I plus 1 comma j. I hope it makes sense. So what I'm doing, I am making a bigger problem and reducing it to two smaller problems here, right? How am I doing that? I am saying, if I wanted to figure out, let me just take a minute more so that everybody appreciates what dp solutions are. Just give me a minute more. Okay, so this actually represented number of ways to reach end from I comma j. I can potentially write this as, this will be equal to number of ways to reach end from A plus the number of ways to reach end from B. Does it make sense? There are two ways here. If you can divide your bigger problem into smaller problems, this is how you would want to do it. And the moment you understand it, you understand how a DP solution very beautifully captures this thing and solves it for us, right? So I have just written dp of I comma j would be equal to dp of I comma j plus 1 plus dp of I plus 1 comma j. Okay, cool. Now this is what my recurrence relationship looks like. Let me just write it. dp of I comma j would be equal to dp of I plus 1 comma j plus dp of I comma j plus 1. Now this is my recurrence relationship. Now looking at this recurrence relationship, I would want you guys to answer, and also looking at the definition that a state here means, I would want you guys to answer what state will give me the final answer. Guys, answer that for me. If my state dpij represents the number of ways to reach from I comma j to end, what state will represent the final answer for me? I'm pretty sure that you guys would be able to figure out that the final answer would be given by dp of 0 comma 0, right? Because I actually want to reach from the 0 comma 0th index to the end. So this state will give me the final answer. So this will be my final answer. Now what is remaining? The base cases are remaining. So let's try to look at the base cases here. Look at this recurrence again. Figure out which particular states will not be able to define, we will not be able to define using this recurrence relationship. Okay, so try to understand that. This is what my states ka matrix looks like. At every point in time I am going to the right and going to the down. So tell me for which states it will not be possible to go to the right or go to the down. If I am not wrong, these are the states where I will not be able to go towards the right, and these are the states where I will not be able to go towards the down. Does it make sense? So it means that these states are not, we cannot explain these states using this recurrence relationship. So all these states should be our base cases. Does it make sense to everybody? All these states should be our base cases, and to find find the answer to them, it's very trivial. Base cases are very trivial to answer. You guys tell me, what will be the answer for this dp of this state? It will be 1, right? Because I just need to figure out the number of ways of reaching from this cell to this cell only. It will be 1. Tell me for this cell, number of ways to reach from this cell to the end. Again 1. So for all these cells, the number of ways is going to be 1. There is only one option that you can take. Just take down, down, down and reach the end, right? Because there is no right to take. Similarly, for all these cells, again the options are only 1, because you can only take right, right, right. There is no option to go down. Okay, so these are the base cases that I have, and all of them are initialized by 1. The moment you do it and you write this recurrence relationship, you solve your question. Does it make sense to everybody in the class? I hope it does. Let's move to the next question that we wanted to discuss now. If there is anyone who's feeling any confused, you can feel free to let me know. Okay, cool. Now let's actually move to the third question of today, and which is just a simple modification of the problem that we just saw. Okay, now the problem is that you still have a matrix at hand. Let's build a matrix: 72105 57128, let's say 68239, let's say 15351, and let's say 29470. So you still have a matrix at hand. But you will see that the matrix now has numbers filled in it. What does these numbers represent? The numbers, Abhishek, I will share the code with you after the class, because I wanted to cover more concepts, and writing the code will only take time and I won't allow me to cover more concepts. Do not worry, I will share the code once the class ends, and I will attach them to the description. Okay, cool. Now let's come back to this. We have this matrix. Now again we want to reach from the starting cell, and we want to reach the ending cell. Okay, the problem is still the same, that you want to reach from the starting cell to the ending cell, but it's not as if you want to figure out the number of ways. The problem now is that you need to figure out the minimum cost path from the start cell to the end cell. What does that mean? It means that whatever path you take, whatever path you take, and whatever cell you visit, the cost of that path is the summation of all the cells that you visit. Okay, so cost of path you take from start to end is equal to the summation of cost of every cell that you visit. This is the problem that you have, and you want to minimize this cost. You want to print what is the minimum cost that you could have had if you wanted to solve this question, reach from the start to the end. Okay, this is what the question is. Now, again, from any cell, you can either move to the right cell or the down cell. These are the only two options that you have. Do you guys think that just by looking at the things that we solved, that we did for the last problem, can you actually solve this problem as well? Can you actually solve this problem as well? Let's try to look at again those 3 points and see how we can answer those 3 points to get a solution to this problem. Okay, the first point was how to best represent a state here. I would say you can still represent the state here using the same approach as we did there. You can say min c, which is minimum cost of I comma j, will tell you the minimum cost of path from I comma j to end. Let's say this is what my state represents. This is the answer to the first question. Okay. Secondly, let's look at the answer to the second question. The answer to the second question was what parameters do you require to represent a state? Again, the parameters here would be I comma j. These are the parameters that are required. The answer question 3 was what is the element of choice that I have? The element of choice that I have is again that you can either go to a right or you can go towards your down. Cool. Again, are these two elements of choice mutually exclusive and exhaustive? Yes, these are again mutually exclusive and exhaustive. Okay, so let's try to define a recurrence here. I would say that if I am at a minimum cost I comma j, if I want to find the answer to this, I would tell you that there were two options, either to move towards the right or to move towards the down. If I move towards the right, the sub problem that I will be having would be minimum cost I comma sorry I plus I comma j plus 1. Okay, and if I move towards my down, the sub problem would be minimum cost I plus 1 comma j. Does it make sense, folks? There are two options. If I actually take the path towards my right, this is what my question is going to look like. If I take the path towards my down, this is what my question is going to look like. But is do you think, and if I want to find the minimum cost, which path will I take, folks? Let's say I know that from I comma j to reach the end, there are two options that I have. Either I can go towards my right or I can go towards my down. These are the two options that I have. Both will take me towards the end, but both will have different costs. How will I get those costs? I will get those costs using this dp function. Which path should I take, folks? If I want to minimize my answer, which path should I take? The path that gives me the minimum cost. I should take that path. So I will just do a minimum operation on the answers of these two DPs. Does that make sense to everybody? I will just take the path which is the minimum out of these two. Okay. And whatever path is the minimum, I will just add the cost of being at the I comma j cell. Right? Because I am at the I comma j cell, I will just take the cost of that cell. If I add these two things, I will get the DP solution to minimum I comma j. And this is how I represent it. This is how I represent it. This is how I represent it. Then I can just say that the final answer to this question would again be minimum cost of 0 comma 0. I hope this question is also clear to everybody. Abhishek, you have one doubt, but being this being a YouTube medium, I cannot unmute you. You can just write it. Uh, Saryanhu, I will also look at your doubt and try to answer it at the end. Okay. So Abhishek, yes, that is added, right? So you see cost of I comma j I have added. Cool. And I will try to answer that at the end of the lecture, Suryanshu. What is meant by the cost? Okay, Rahul, by cost, I simply mean that if you actually go to a cell, whatever, whatever is the number written at that cell, that is the cost that you have to incur. Okay, cool. Now, Abhishek says, please explain the base cases for me. Okay, Abhishek. So look at the recurrence again and try to look at the states which you will not be able to explain using the recurrence. Okay, try to answer that. So let's say this is what my numbers look like. Let's say this is what my numbers look like. Would you agree that only these are the cells, that is the bottommost cells and the rightmost cells, I cannot explain using this recurrence, because my recurrence wants me to take me to the right and the down, and I will not be able to take the right for these cells, and I will not be able to take the down for these cells, right? And now I want to figure out the minimum cost of reaching from any element till the end. This is what my DP states represent. So let me build my DP array here, and let me try to full, fulfill my DP answers to these base cases. So I will tell you that if you want to reach the end from this cell and it's this cell's cost is 0, the total cost of that path will be 0. So the DP solution to this cell would be 0. Now you tell me, if I want to reach the end from this cell to this cell, what will be the DP solution? It will be get the cost at this and then take the answer for the remaining. So it will be 1. Here it will be 10. 9 plus 1 is 10. Here it will be 18 because 8 plus 10 is 18. And here it will be 23 because 5 plus 18 is 23. Similarly, for this particular row, the answer at this cell will be 7. This cell will be 14. This cell would be 18. This cell would be 27. And this cell would be 29. I hope it makes sense to everybody. Cool. Let's actually move to the next question that we want to discuss today. I hope this is crystal clear to everybody. Now there are several questions that I could have discussed, and we have already have had 1 hour of class. We have already had 1 hour of class. So let me just take maybe one question today, and the remaining questions we are going to take after the in the next session. Okay. So you guys tell me, do you want to take a relatively tougher problem? Do you want me to take a problem which is going to take, let's say, 30-40 minutes to discuss, or do you want me to do it in the next class? I would say that it's 1 hour already into the lecture. Let's take not that tough problem in today's class. Let's discuss that in the next session. Okay. So let me take a relatively simpler problem, but a problem which is very widely used and the concept is very, very important. So we want to take it. Okay. So Abhishek has a question. Can I solve this problem greedily? The problem that we just said. This problem cannot be explained greedily. The reason being is that greedy solutions basically mean that you can take a decision which path to take without looking at what holds for you in the future. Abhishek or everybody in the class answer this, that if you are at, let's say, at this point, let's say you are at this point at 7, can you take a decision of which path that you can choose? So you can either choose a path that takes you to this 1 cell or the path that takes you to this 8 cell. Can you make a decision that from 7 you should always go to 1 because 1 is a smaller number? You cannot do that, right? Why you cannot do that? You cannot do that because 7 to 1, you are only encountering plus 1 to go to 1, but you never know. Maybe the path from 1 to the end will be very, very costly. So you cannot take a decision here without looking at what holds for you in the future. So that is why you cannot actually solve it using a greedy solution. You need to actually know what happens for you in the future. So a greedy solution here would not be possible. Okay. But at the same time, once you know whatever happens thereafter in the matrix and you have stored the answers to them, then you can simply take the choice which will give you the minimum answer till the end, and that's perfectly fine, and that's exactly what we did in this solution. Okay, so I see 2-3 of you saying that let's pick the tougher problem. Okay, so let me pick the tougher problem, but in that case I would want you guys to maybe if we cannot complete it in this session, we would be taking up in the next session, completing in the next session. Let's but start with that relatively tougher problem. Okay, cool. So the problem is as follows. The problem is as follows, that let's assume that you can buy and sell one stock. Okay, Alok, I can explain that to you after the end of the class. So just hang on for a bit. Let me define this problem, try to solve this, and then I can try to answer your question as well. Cool. So the problem here is that you, let's say, are given the prices of a share at every day. Okay, so let's say this is day 1, day 2, day 3, and so forth, so on and so forth. So let's say the price of that share on day 1 is $3. It's $3 on the second day. Let's say let's talk in rupees. It's ₹5 on the third day. It's zero on the fourth, zero on the fifth. Let's say ₹3 on the sixth, ₹1 on the fourth, and ₹4 on the last. Does it make sense? So you basically have the prices of these shares at different days. Now the question is that you can essentially buy this share and sell this share. Let's call that buying and selling a pair a transaction. So you can perform some transactions here. Transactions basically mean a pair or a tuple of buy and sell. So you can buy a share and sell it. And notice that there are no put call options here. You can only sell it when you have bought it before. So you can buy a share on one particular day, sell it on some other particular day. Does it make sense, folks? And you can repeat this transaction, let's say k times. You can repeat this transaction k time. But the constraint is that you cannot say that I will buy it twice before I sell it once. So the moment you buy it, the only option that you have now is to sell it. When you will sell it, only then you can buy it. What does that mean mathematically? It means that at any given point in time, you can only hold 1 unit of stock. Okay, so the condition here is at any given point in time, you can hold at most one stock unit. So you cannot just buy twice and then sell it. So you will, the moment you buy it, the first thing that you should do thereafter is to sell it. Only then you can buy it again. Okay, cool. So this is one condition. The second condition that you have is that you will always first buy and then sell. So you will always first buy and then sell. Does the question make sense to everybody? Right. So these are the two conditions. We want to figure out the maximum profit. You want to figure out the maximum profit that you can do after at most k transactions. This is what the question wants you to figure out. Cool. This is the question that we have. Let's now try to look at a very simple case. Let's assume, let's look at a very simpler problem. This is a problem actually is that you can actually do k transactions, at most k transactions. The simpler problem would be, what if k is exactly equal to 1? What if you can only do one transaction? Can we try to figure out an answer to that? Can we try to figure out an answer to saying that what would be the best way if I could only have done one transaction? That is one buy and one sell. So let me just write the array once again: 3 3 5 0 0 3 1 4. Okay, so let's look at this array and say I can only buy it once and I can only sell it once. What would be the maximum profit that I could have got? Okay, now you folks tell me, if you would want to maximize your profit, you would want to buy at the lowest price and sell at the highest price. Does that make sense? You would want to buy at the lowest price and sell at the highest price. So you will want to buy at lowest possible plus sell at highest possible. Now this is what intuition that you guys would be getting, but can you actually just figure out the maximum from the array and from it subtract the minimum of the array? You cannot do that, right? Because the problem is, if you just look at the maximum of the array and the minimum of the array, there is one more condition that you must buy it before you can sell it. But if you just look at the maximum and the minimum, the problem would be that you can essentially have a problem where you are buying in the future and selling right now. I hope it makes sense to everybody. Let me take a very simple example where you would realize that, that is not possible. So let's assume the stocks, there are only 2 days. The stock was priced 7 units on the first day and 5 units on the second day. Now you want to figure out the maximum profit that you can have if you can buy it once and sell it once. The answer to this problem would be zero. That you would not want to buy it at all and not want to sell it at all, because the price is a decreasing trend and you cannot buy it at 7 and sell it at 5 and make a profit. So you would prefer not to buy it, and the answer would be zero. But if you just take the maximum here would be 7 and the minimum here would be 5. If you just subtract the max minus min, it will be 7 minus 5, which will give you 2 units of profit. But that's a wrong answer to take. You are right, you cannot have 2 units of profit because you need to buy it before you can sell it. So the answer to this would be 0 and not 2. So you realize that you cannot simply find the maximum and the minimum from the array and just subtract them to figure out the answer. I hope this is clear to everybody that this solution will not work. Now, the point is that we would want to somehow figure out the solution. This simple greedy approach will not work. What will we do now? My summation is that let's look at the array properly. Okay, my summation is let's look at the array properly and try to figure out some pattern. I would say let's store two states here. One state here is, one state here would be, what is the minimum price at which I can buy it, assuming I bought in the first I days. Does it make sense? The first state that I would want to have is minimum I, which will say what is the minimum price at which I could have bought it if I was buying it in the first I days. Does it make sense? Minimum price at which I could have bought it if I bought in the first I days. Does it make sense? So you folks tell me, if I can buy in the first 1 day, what is the minimum price? It would be 3. What is the minimum price if I can buy in the first 2 days? Again 3. What is the minimum price that I can buy in the first 3 days? Again 3, because I could have bought at price 5, but I can already I can buy at price 3, so I would want to buy at 3 and not at 5. Okay, then till the day 4, what is the minimum price at which you can buy it? It's 0. Till 5, what is the minimum price at which you can buy it? It's 0. Till 6, what is the minimum price? Again 0. 7, minimum price, again 0. 8, minimum price, again 0. Does this make sense to everybody in the class? The minimum price at which you can buy till the ith position. Folks, please be responsive. Please let me know if you can get it, you cannot get it, so that I know how quickly to move and how slowly to move. Okay, so this is how you would figure out if what is the minimum price at which you can buy it. Let me now also compute an array for you, which is the maximum price till the ith index if I wanted to sell it. Does it make sense, folks? What is the maximum price till the ith index if I wanted to sell it? But this array, this minimum I represented it from 0 to I. The maximum I will want to represent it from I to n minus 1. So I want to figure out that what is the maximum price at which I could have bought it from the end. So you would tell me, if I want to fill it from the end, it would be 4 that I can sell it at 4. It would be still 4 that I can sell it at 4. It would be still 4 that I can sell it at 4. 4, 4, and now it becomes 5 because I would prefer to sell it at 5. 5 and 5. So this is what my array looks like if I look at from the end till that point in time. Now, just because I want my buy to be first and sell to be later, I can essentially go to every index now and look at a difference between min I and max I, and I will get the subtract. So I will subtract them and get the answer. Why will that work? Because if I look at any I here, it will mean that the minimum price at which you could have bought it from the starting till this point is 0, and the maximum price at which you could have sold it from the end till this point is 4. And these two things together satisfy all the conditions. You are buying first, selling later, and you are buying at the minimum price, selling at the maximum price. So what will you do? You will just traverse over this array and figure out the difference between max I and min I in all these indexes. So what will I do? Let me just rub a few things here so that things are clear to you and you can understand it properly. So let me just rub a few things here, and now let me show to you the difference array. Okay, so let's look at the difference array. The difference between here and here would be 2. That if I want to do it at the first index, it would be 2, second index 2, third index 2, fourth index 4, fifth index 4, sixth index 4, seventh index 4, and eighth index 4. What is the maximum out of all of them? The maximum out of all of them would be 4. So you can potentially say that the maximum profit that you can have, if you can only do this transaction once, it would be 4. Does that make sense to everybody in the class? Abhishek, the answer that you are saying will not suffice. Think about it, take it as a homework, and try to figure out why that will not work. Okay. Also, let so I'm assuming that this becomes very clear to everybody that if k was equal to 1, how to solve this problem. The next thing that we wanted to do was look at k is equal to 2. If you can do an operation twice, if you can buy, sell, and again buy and sell, what would be the maximum profit? But let's do it in the next class. And then we would want to optimize it to answer for any generic k, that if I can perform a transaction k times, what would be the best answer that I can get? And we are going to discuss these two things in the next session. Does that make sense to everybody? I hope you guys enjoyed the session. The folks who want to leave it now can very well leave it. Thanks a lot for attending. I hope you guys enjoyed it. And yeah, so let's actually see. Hope to see you again in the next session. For the people who have some doubts, they can stay back, and you can just tell me what is the doubt that you can have, and I can just try to resolve those doubts. Abhishek, take it as a homework. Your friends have helped you. Take it as a homework, but that solution will not work. Okay, try to figure out why that solution will not work. Before that, do you understand that this solution will work? I hope you understand that this solution will work. Okay, so where can I practice? So you can practice at interviewbit.com/practice. So let me just you guys would already be knowing that, but let me just still share that screen once again and tell you. Yes, this was DP, right? Don't you think, Harshit, this was DP? This was DP, right? Because what we are doing, we are essentially trying to look at the answers to smaller problems and try to solve it. Let's look at interviewbit.com/practice. You can go to the programming tab, and here you can go to DP if you want to solve questions of DP. And here you would see that the questions are segregated based on concepts. So you will see a simple array DP questions there. You will see greedy or DP, where you can actually have a doubt between whether a greedy solution will work or a DP solution will work. Here DP tricky, matrix DP, suffix prefix DP, ad hoc, knapsack. So you can see so many problems, so many options there, and you can practice whatever problem you want to. And yep, cool. uh, can we end the session here now? Thanks a lot for attending, folks. I really enjoyed interacting with you. I hope you also enjoyed it. And the next session most likely would be on it, for sure would be next week, and most likely the day would be Friday. So let's have these DP Friday sessions till the time we are in this lockdown, so that during this lockdown period you can actually make the most out of this period and try to hone your skills and be better and better at DP. Okay. Ashish Kumar Bhattacharya asked a question that how to classify a problem between DP or a greedy. So Ashish, if you have looked at my first session that I took the last week, you would realize that I discussed that greedy solutions are those in which you can just take a decision for the global optima by looking at just the information that you have right now. Looking at the information right now, taking a solution for the entire global maximization is what greedy solutions generally allow you to do. That irrespective whatever happens in the future, you can take a decision right now by looking at what you have right now. DP solutions, on the other hand, say that without looking at what holds for you in the future, you can never take a decision right now, which will definitely lead you to the global optimum. I hope that makes sense, Ashish. If it does not, you can look at the first video. And if it still does not, you can ask me in the next session. Okay. Alok says, please do post some codes too. For sure, Alok. All the problems that we discussed in today's lecture, And in the first session, I am going to post the solutions of all those problems. Harshit, my name is Tarun Malhotra, and I would be happy to connect you over with you over LinkedIn. You can just send me a request if you want to connect with me. Yeah, thanks a lot, everybody. Thanks a lot for attending. Hope to see you again in the next session. See you. Goodbye.